Right now, the light entering your eyes from the night sky left its source before your grandparents were born. Some of it left before the first human being ever walked the surface of this planet. Some of it left before our species existed at all. You are not looking at the sky as it is. You are looking at the sky as it was. The universe you see above you is a fossil record written in light, and every single photon that reaches your eye is a message from the past, traveling at the only speed the universe permits. That speed is 186,282 miles per second. In the time it takes you to blink, light travels roughly 11,000 miles. In 1 second, it circles the Earth 7.5 times. In 8 minutes, it crosses the 93 million miles between the Sun and this planet. These numbers sound fast. They feel fast. They are, by every measure available to human experience, incomprehensibly fast. And yet, the nearest star beyond our Sun, a dim red dwarf called Proxima Centauri, sits 4.24 light-years away. That means light, traveling at 186,282 miles per second, requires 4 years and 3 months to complete the journey. Not a spacecraft, not a rocket. Light itself, the fastest thing in the universe, needs 4 years to reach our closest neighbor. If you shrank the distance between the Earth and the Sun down to the length of a single inch, Proxima Centauri would sit roughly 4.5 miles away. You would need to walk across an entire city just to reach the nearest star in this scale model, and the Sun would be a tiny dot beneath your fingertip. Now extend that scale outward. Our galaxy, the Milky Way, is approximately 100,000 light-years across. On the same scale where the Earth-Sun distance is 1 inch, the Milky Way would stretch 1.6 billion miles. That is the distance from Earth to Saturn. Our entire galaxy, compressed to a scale where you could hold the solar system between your fingers, would still be too large to fit within our own solar system. And the Milky Way is one galaxy among an estimated 2 trillion in the observable universe. The Andromeda Galaxy, our nearest large galactic neighbor, lies 2.537 million light-years away. The light you see from Andromeda on a clear night left that galaxy before the first stone tools were being made on Earth, before Homo sapiens existed, before our evolutionary ancestors had yet developed anything we would recognize as human thought. That light has been traveling through the void for 2.5 million years, and is only now, tonight, arriving at your eye. The edge of the observable universe sits approximately 46 billion light-years away in every direction. Not because the universe is only 46 billion light-years in size, but because that is the farthest distance from which light has had time to reach us since the beginning of everything. Beyond that horizon, there is almost certainly more universe, perhaps infinitely more, but we cannot see it. The light from those regions has not yet had time to arrive. The universe is older than 13.8 billion years, and yet its observable edge is 46 billion light-years away, because space itself has been expanding during all the time that light was traveling toward us. These distances do not simply represent a logistical inconvenience. They represent something more fundamental. They represent a kind of imprisonment. If you launched a spacecraft today, using the most powerful propulsion system humanity has ever built, the Space Launch System at its theoretical maximum, your ship would travel at roughly 36,000 miles per hour. At that speed, the journey to Proxima Centauri would take approximately 80,000 years. Not generations, not centuries, 80,000 years. The last ice age ended 11,700 years ago. Modern human civilization, everything from the first cities to smartphones to this moment, fits comfortably within 10,000 years. We would need 8 times the entire span of recorded human history just to reach the nearest star, and then another 80,000 years to return. Every star you see in the night sky is, by this measure, forever unreachable. This is the problem that has haunted physicists, philosophers, and dreamers since the moment we understood what those points of light actually were. Not lanterns hung in a dome above the Earth, not holes in a celestial curtain, but suns, other suns, some of them larger and brighter than our own, each one potentially warming its own worlds, its own oceans, its own forms of life. and every single one of them separated from us by distances so vast that no human being, no machine we have ever built, no technology we currently possess could ever bridge the gap within any time frame that matters to a living thing. The universe is, on any practical scale, unreachable. But here is what most people miss when they hear this. The laws of physics that establish this prison are the same laws that contain, hidden within their mathematics, a theoretical key. The equations that make faster-than-light travel seem impossible also describe, in precise mathematical language, mechanisms by which that impossibility might be circumvented. Not broken, not violated, circumvented. The distinction matters enormously, and it is the subject of some of the most serious and rigorous physics being done today. This is not science fiction. The scientists working on these ideas are not writing novels or screenplays. They are writing equations, submitting papers to peer-reviewed journals, presenting results at conferences attended by the most careful and skeptical minds in physics. They are asking a question that has no certain answer yet, a question that sits at the very boundary of human knowledge, where our best theories begin to strain and crack under their own weight. The question is this: is the speed of light a true absolute limit, a feature of reality so fundamental that no conceivable technology could ever overcome it? Or is it a barrier, something formidable and perhaps practically insurmountable with our current knowledge, but not necessarily the final word on what the universe permits? We do not know the answer. That is the honest truth. After more than a century of testing, after particle accelerators and atomic clocks and GPS satellites and gravitational wave detectors, after every experiment we have been able to devise, we have confirmed the speed limit again and again. Nothing has exceeded it. Nothing has even approached it, except in the most extreme conditions we can create in laboratories, and even there, the limit holds. And yet the equations whisper something else. If you enjoy spending time at the edge of what is known, in the territory where physics becomes philosophy and certainty gives way to possibility, then do me a simple favor and hit that like button and subscribe. It genuinely helps this channel reach more people who ask these kinds of questions. And there is no better company for a journey like this one. Make yourself comfortable. Turn off the lights if you like. Let the room grow dark around you the way space is dark, vast and silent and full of distances that have no end. Let's begin. The story of the speed of light as a limit begins not with a telescope or a particle accelerator, but with a young man sitting alone in a patent office in Bern, Switzerland in the year 1905. He was 26 years old. He had recently failed to obtain an academic position despite earning his doctorate. He was reviewing other people's inventions for a living, spending his days assessing the technical merits of mechanical devices and electrical patents. By any conventional measure, he was not yet a person of consequence. His name was Albert Einstein, and in that same year, between patent reviews, he published 4 papers that restructured the foundations of physics so completely that the science before and after 1905 are almost unrecognizable as the same discipline. One of those papers introduced the world to what we now call special relativity, and at its heart was a single, strange, almost offensive claim. The speed of light is constant, always, for every observer, regardless of how fast the observer is moving, regardless of how fast the source of the light is moving, regardless of any other conditions whatsoever. The speed of light in a vacuum is always 186,282 miles per second. It never varies. It cannot vary. It is not simply fast. It is fixed. This sounds reasonable until you think about it carefully. Then it sounds impossible. Here is why. Imagine you are standing beside a road and a car passes you moving at 60 miles per hour. The driver throws a baseball forward at 40 miles per hour relative to the car. From your perspective, standing still beside the road, the baseball is moving at 100 miles per hour. The speeds add. This is intuitive. This is how the world works at everyday scales. Galileo understood this in the 17th century. Newton formalized it. It is the most basic rule of motion. Now replace the baseball with a beam of light. A spaceship passes you at half the speed of light, 93,000 miles per second, and shines a flashlight forward. By the same logic that gave you 100 miles per hour for the baseball, The light should be moving away from you at 1.5 times the speed of light. 1/2 plus 1 whole. The speeds should add. They do not. The light moves away from you at exactly 186,282 miles per second. The same speed it always moves. The same speed it would move if the ship were standing still. The motion of the ship adds nothing to the speed of the light. 0. The speeds do not add. Einstein's radical insight was not merely to accept this strange experimental fact, which had been stubbornly confirmed by the Michelson-Morley experiment in 1887, and which physicists had been struggling to explain for nearly 2 decades. His insight was to follow it to its logical conclusion, no matter how disturbing that conclusion turned out to be. If the speed of light is truly constant for all observers, then space and time cannot be the fixed, absolute, universal stage that Newton imagined. They must be flexible. They must adjust themselves, bend and stretch and compress in precisely the way needed to ensure that every observer always measures light moving at the same speed. And this is exactly what happens. When you move at high speed, time runs slower for you relative to someone standing still. This is not a perception. It is not a psychological effect of travel. It is a real, physical, measurable change in the rate at which time passes. If you travel at 90% of the speed of light, time runs for you at roughly 44% of the rate it runs for someone at rest. For every year that passes on Earth, only about 5.5 months pass for you on your fast-moving ship. We have measured this. Atomic clocks flown on airplanes tick at a slightly different rate than identical clocks left on the ground. The difference is tiny at aircraft speeds, nanoseconds per hour, but it is real, and it matches Einstein's predictions exactly. GPS satellites orbit the Earth at speeds high enough and at altitudes different enough that their onboard clocks run at a measurably different rate than clocks on the surface. The GPS system must account for this relativistic time difference. If it did not, your navigation app would accumulate errors of several miles per day. Every time you use GPS, you are relying on Einstein being correct about time dilation. Space compresses as well. A ruler moving at high speed is physically shorter in the direction of motion than the same ruler at rest. Not because it is being squeezed by some force, but because the geometry of space-time itself changes with velocity. At 90% of the speed of light, lengths in the direction of travel compress to about 44% of their rest value. And mass, or more precisely the energy required to accelerate something further, increases. As an object approaches the speed of light, it becomes harder and harder to push. Not because of friction or any conventional resistance, but because the energy you pour into acceleration increasingly goes not into increasing speed, but into increasing the object's relativistic energy, its effective inertia. The faster it goes, the more energy each additional increment of speed requires. At 99% of the speed of light, you need roughly 7 times as much energy to accelerate as you would at rest. At 99.9%, 22 times as much. At 99.99%, 70 times as much. The curve is asymptotic. As you approach the speed of light, the energy required approaches infinity. To reach the speed of light, an object with any mass at all would require an infinite amount of energy. There is not that much energy in the universe. There is not that much energy in any conceivable universe. The barrier is not an engineering problem. It is a mathematical absolute written into the structure of reality. This has been tested in particle accelerators with a thoroughness that borders on obsessive. The Large Hadron Collider at CERN accelerates protons to 99.9999991% of the speed of light. At that speed, a proton is traveling fast enough to circle the collider's 1.7-mile ring 11,245 times per second. Engineers and physicists pour energy into those protons continuously, and the protons get faster, but they get faster more and more slowly, exactly as Einstein predicted, approaching the speed of light on a curve that never quite touches it. The protons never reach it. They never will. No matter how much energy you add, you can always add more and still fall short. The limit is absolute. But Einstein's equations describe more than the behavior of objects moving through space. They describe the behavior of space itself. And space, it turns out, is not a passive backdrop. It is a dynamic, physical entity that can warp and bend and curve in response to mass and energy. It can expand, it can contract, and crucially, there is no equation in all of general relativity that places any limit on the speed at which space itself can change. Objects cannot move through space faster than light. That limit is ironclad, but space itself has no such restriction. The stage can move at any speed it chooses, and anything sitting on that stage moves with it, not by traveling through space, but by being carried by space. We know this is true because we observe it happening right now, in every direction, at every moment. The universe is expanding. Every galaxy beyond our local group is moving away from us, and the farther away it is, the faster it recedes. Galaxies roughly 14 billion light-years away are currently receding from us at approximately the speed of light. Galaxies farther than that are receding faster than light, not because they are moving through space at superluminal speeds, but because the space between us and them is expanding, stretching, growing larger at a rate that, at sufficient distances, exceeds 186,282 miles per second. Those galaxies are not violating Einstein's speed limit. Nothing in them is moving through local space faster than light. The space itself is simply expanding faster than light can cross it. The galaxies are, in a very real sense, stationary. Space is what is moving, and if space can move faster than light naturally, spontaneously, as a fundamental feature of the universe we inhabit, then the question becomes almost unavoidable. Could we make it move on purpose? The year was 1994. A young physicist named Miguel Alcubierre was sitting in his office at the University of Wales, and he was watching Star Trek. This is not an unusual thing for a physicist to do. Science fiction has always maintained a complicated relationship with the people who actually work on the science, sometimes inspiring them, sometimes frustrating them with its casual disregard for the laws of physics, and occasionally, very occasionally, prompting them to ask a question that no one had thought to ask before. Alcubierre was watching the Starship Enterprise travel at warp speed, and instead of accepting the fictional technology as a convenient narrative device, as most viewers do, he asked the question that only a physicist would ask. Could this actually work? Not the fictional version, not the technobabble about dilithium crystals and warp cores, the real version, a mathematically rigorous version derived from equations we know are correct. He was not asking whether we had the technology to build such a thing. He was asking something more fundamental. Do the laws of physics, as we currently understand them, permit the existence of such a thing in principle? He sat down with Einstein's field equations, the same equations that describe black holes and the expansion of the universe and the bending of light around massive objects, and he began to work. What he found surprised him. What it did to the physics community was something closer to a quiet earthquake. Alcubierre published his result in the journal Classical and Quantum Gravity in 1994 in a paper titled simply The Warp Drive, Hyper-Fast Travel Within General Relativity. The title itself was a kind of provocation. Hyper-fast travel within general relativity, not in spite of general relativity, not by violating general relativity, within it, using it, harnessing the same mathematical framework that seemingly forbids faster-than-light travel to describe a mechanism that achieves exactly that result. The key insight was the one we arrived at the end of the last section. Objects cannot move through space faster than light, but space itself can move at any speed. So instead of trying to push a spacecraft through space at superluminal velocities, which is impossible, what if you left the spacecraft perfectly still and moved the space around it? Let me be precise about what this means, because the precision matters. Alcubierre's proposal was to engineer a specific configuration of space-time around a spacecraft. In front of the ship, space would be compressed, contracted, made smaller. The distance between the ship and its destination would physically shrink. Behind the ship, space would be expanded, stretched, made larger. The ship itself would sit inside a bubble of flat, normal space-time, completely undisturbed, experiencing nothing unusual at all. Think of it this way. Imagine you are standing on a moving walkway at an airport. You are not walking, your legs are still, your feet are not pushing against the ground in the way they would if you were walking across a normal floor. You are simply standing, and yet you are moving, you are covering distance. The walkway beneath you is what is moving, and you are being carried by it. From your perspective, you are stationary. From the perspective of someone standing beside the walkway watching you pass, you are traveling at whatever speed the walkway moves. The Alcubierre drive works on exactly this principle, but instead of a mechanical walkway, the thing that is moving is space itself. The warp bubble contracts the space ahead of the ship, effectively pulling the destination closer, and expands the space behind the ship, pushing the origin farther away. The ship surfs on this wave of contracting and expanding space-time. It does not travel through space at all. Space travels around it. From inside the bubble, the experience would be entirely unremarkable. No acceleration, no crushing G-forces, no sensation of movement whatsoever. The passengers could walk around, drink coffee, sleep, read, have an entirely ordinary experience of time passing at its normal rate. They would not age differently than people back on Earth. They would not experience the time dilation that makes conventional near-light-speed travel so problematic for long journeys. Because they are not moving through space, the relativistic effects that depend on velocity through space simply do not apply to them. From outside the bubble, from the perspective of a stationary observer watching the ship depart, the ship would appear to travel faster than light. It would cover light years of distance in a time that, by any conventional measure, should be impossible. A journey to Proxima Centauri that would take light itself 4 years and 3 months would, depending on the intensity of the warp field, potentially take days or weeks or less. And none of this violates Einstein's speed limit. Nothing inside the bubble is moving through space faster than light. The passengers are not moving at all. The ship is not moving relative to the space immediately surrounding it. The space itself is what is moving, and space has no speed limit. This is not a loophole in some informal or sloppy sense. It is a genuine, mathematically rigorous feature of general relativity. The same theory that forbids objects from moving through space faster than light explicitly permits space itself to expand and contract at any rate. We have been observing this for decades in the large-scale structure of the universe. The expansion of space at cosmological distances is not a hypothetical. It is measured, confirmed, and incorporated into the standard model of cosmology. Galaxies are not flying apart through space. Space between them is growing. The Alcubierre drive proposes to do locally, on a small scale, around a single spacecraft, what the universe does naturally on the largest possible scales. When Alcubierre published this result, the response from the physics community was unusual. There was no immediate dismissal, no reflexive rejection of the idea as science fiction dressed in mathematical clothing, because it was not. The mathematics was clean, the derivation was rigorous, the metric he wrote down, the precise mathematical description of how spacetime would need to be shaped to achieve this effect, was a valid solution to Einstein's field equations. You could verify it yourself if you were fluent in the language of differential geometry and tensor calculus. The equations checked out. Physicists who worked through the paper found themselves in a strange position. They could not say it was wrong. The math was correct. What they could say was that it raised questions, serious, difficult, potentially devastating questions about whether such a solution could actually be realized in the physical universe, whether the mathematics, as beautiful and consistent as it was, corresponded to anything that could actually exist. These questions, and the decades of work that followed in attempting to answer them, are where the story becomes not just scientifically fascinating but philosophically profound. But before we get to the problems, it is worth sitting with the wonder of what Alcubierre actually demonstrated. He showed that Einstein's own equations, the equations that appear to imprison us at sublight speeds forever, contain within them a description of a machine that could take us to the stars. Not in defiance of physics, in accordance with it. He did not find a way to break the rules. He found a rule that had been there all along, unnoticed, waiting to be seen. Think about what that means for a moment. For nearly a century after Einstein published his work, physicists believed the message was clear. You cannot travel faster than light, full stop. The equations said so. The experiments confirmed it. The conclusions seemed unavoidable. And then a graduate student watching a television program asked a slightly different question and found that the same equations, read from a different angle, told a different story. Not a contradictory story. The same story, but with a chapter that everyone had overlooked. This happens in physics more often than people realize. The equations contain more than we know how to extract from them at any given moment. General relativity predicted black holes before anyone believed they could actually exist. Einstein himself did not believe they were real, despite having written the equations that required them. It predicted gravitational waves, ripples in the fabric of space-time caused by accelerating masses, and for decades, physicists debated whether these were real physical phenomena or merely mathematical artifacts. In 2015, the LIGO detector felt a distortion in space-time smaller than 1/10,000th the diameter of a proton, caused by two black holes colliding 1.3 billion light-years away, and confirmed that gravitational waves were real. The equations knew before the physicists did, and Alcubierre's metric suggested that the equations knew something else as well, that the speed limit, real and absolute as it is for objects moving through space, was not the final word on how fast a ship could cross the distance between stars. The mechanism, to be precise about it, involves what mathematicians call a metric, a mathematical object that describes the geometry of space-time. The geometry of space-time determines how distances are measured, how time flows, how things move. Ordinary flat space-time, the kind you experience sitting in a room, has a simple metric. The distances are just what you would calculate with ordinary geometry. The space-time around a massive object like a star or a black hole has a curved metric. Distances and times are distorted by the curvature of space-time caused by the mass. Alcubierre wrote down a metric that described a region of space-time with a very specific, very unusual shape. Ahead of a central point, the metric described space that was compressed, contracted, so that distances in the direction of travel were shorter than they would normally be. Behind the central point, the metric described space that was expanded, stretched, so that distances in the direction of travel were longer than they would normally be. At the central point itself, the metric was perfectly flat, normal, undisturbed. Place a spacecraft at the central point and you have an Alcubierre warp bubble. The ship sits in flat space-time. The space ahead contracts toward the destination. The space behind expands away from the origin. The ship is carried forward, not by any force acting on it, but by the geometry of the space-time bubble it inhabits. The rate at which it moves depends on the rate at which the bubble's geometry changes, and there is, in the mathematics, no upper limit on that rate. The bubble can move at any speed, 10 times the speed of light, 1,000 times, 1,000,000. The equations do not object. Space can contract ahead of the ship as fast as you like, carrying the ship with it, without any of the energy requirements that make conventional faster-than-light acceleration impossible. In a warp bubble moving at 10 times the speed of light, a journey to Proxima Centauri would take roughly 5 months. At 100 times the speed of light, 2 weeks. At the speeds described in science fiction, days or hours. The galaxy, on these timescales, becomes accessible. Not merely the nearest few stars, but thousands of stellar systems within practical travel distances. Civilizations could rise and fall in the time it would take a conventional spacecraft to reach even the closest stars. But with a warp drive, you could cross the distance to Proxima Centauri before the seasons change on Earth. This is what the mathematics permits. This is what Alcubierre showed. And then physicists started asking what it would cost. The first question anyone asks about the warp drive is the obvious one. What does it run on? What is the energy source? How much fuel would you need to warp space-time around a spacecraft and sustain that warping for the duration of a journey to another star? Alcubierre's original paper included an estimate. It was not encouraging. To create a warp bubble large enough to contain a spacecraft, perhaps 100 meters across, moving at a speed comparable to the speeds discussed in science fiction, the energy required would be on the order of 10 to the power of 64 joules. That is a 1 followed by 64 zeros. Written out in full, it would occupy most of a printed page. To put this in context, the total energy output of our Sun over its entire 10 billion year lifetime is approximately 10 to the power of 44 joules. The Alcubierre drive in its original formulation would require roughly 10 billion times the total energy output of our Sun across its entire existence, delivered instantaneously to maintain the warp field. The total mass energy of the observable universe, every particle of matter in every star, in every one of the 2 trillion galaxies we can observe, converted entirely to energy through Einstein's equation, amounts to approximately 10 to the power of 69 joules. The original Alcubierre drive would require a significant fraction of all the energy in the observable universe to power a single spacecraft. This is not an engineering challenge. It is not the kind of problem you solve by building a better power plant or discovering a more efficient fuel source. It is, in its original form, a number so large that it renders the proposal physically meaningless. You cannot power a device with more energy than exists in the universe. The universe does not have a surplus of itself to donate to your spacecraft. But physicists did not stop there, because the mathematics allowed refinements. The shape of the warp bubble, the precise geometry of the space-time distortion, was not fixed. Alcubierre had written down one particular configuration, but there were others. Different bubble geometries required different amounts of energy, and some geometries were more efficient than others. In 1999, a physicist named Chris van den Broek published a modification to Alcubierre's original design. The insight was elegant. The energy required to maintain a warp bubble depends largely on the size of the bubble as seen from the outside, the external surface area of the distorted space-time region. Van den Broek proposed making the exterior of the bubble very small, perhaps a few Planck lengths across, the smallest meaningful unit of length in physics, while engineering the interior to be much larger, large enough to comfortably contain a spacecraft. The geometry of the modification was strange, the kind of space-time shape that has no analog in ordinary experience, but it was mathematically valid, and the energy requirement dropped dramatically. Instead of needing a significant fraction of all the energy in the universe, Van den Broek's modified bubble required energy equivalent to roughly the mass of Jupiter, about 2 times 10 to the power of 30 kilograms. Jupiter is the largest planet in our solar system. Its mass is approximately 318 times the mass of Earth. Converting the entire planet Jupiter to energy would yield an almost incomprehensible amount of power. But it is a finite number. It is a number you could in principle write on a single piece of paper without running out of space. And more importantly, it is a number that refers to something that actually exists in the universe. We have a Jupiter. We know where it is. The reduction was staggering, from the mass energy of the observable universe to the mass energy of a single planet. Thousands of orders of magnitude smaller, still impossibly large by any current engineering standard, but small enough to take seriously as a theoretical proposition. Then in 2012, Harold White, a physicist working at NASA's Eagle Works laboratory, the Advanced Propulsion Research Division of the Johnson Space Center, published calculations suggesting the energy requirements could be reduced even further. White's approach focused on the thickness of the warp bubble wall and the shape of the energy distribution within it. By making the bubble wall very thin and oscillating the intensity of the warp field rather than holding it constant, he calculated that the energy requirement could be reduced to approximately the mass energy of 700 kilograms of matter. 700 kilograms, the mass of a small car. Converted to energy through E equals mc squared, this yields approximately 6.3 times 10 to the power of 19 joules. This is still an enormous amount of energy by any ordinary measure, roughly equivalent to the energy released by several thousand nuclear weapons detonated simultaneously. But it is energy that fits within the realm of things we can at least imagine generating. A sufficiently advanced matter-antimatter reactor, of the kind that theoretical physics does not forbid, could in principle produce this much energy. White's calculations were met with both excitement and skepticism. The excitement came from the sheer audacity of the reduction, from the energy of the observable universe to the energy of a compact car, in 3 decades of theoretical refinement. The skepticism came from other physicists examining White's assumptions and finding them, in some cases, difficult to justify. The specific bubble geometries he proposed required space-time configurations that might not be achievable even in principle. The oscillating warp field he described had not been shown to actually reduce the total energy requirement when calculated more carefully. The debate continues. The numbers are disputed. Different calculations using different assumptions yield different results. This is not a settled question, but the trajectory of the research over 30 years points in a consistent direction. The energy requirements for an Alcubierre warp drive, enormous in the original formulation, have been reduced through theoretical refinement again and again. There is no proof that they can be reduced to levels a civilization like ours could achieve, but there is also no proof that they cannot. And then there is the other problem, the one that cannot be solved by optimizing bubble geometry or refining energy calculations, the one that strikes at something more fundamental than engineering. The Alcubierre drive does not simply require energy, it requires a specific kind of energy, a kind of energy that should not, by the rules of everyday physics, exist at all. It requires negative energy. In every experience of ordinary life, energy is positive. A burning log releases positive energy as heat and light. A charged battery stores positive energy that can do work. The food you eat contains positive energy that your body extracts and uses to power every thought you think and every movement you make. Positive energy is what you pay for when you buy electricity. It is what the sun radiates. It is what powers every process in the known universe at every scale from subatomic to cosmic. Negative energy sounds like an invention, like something a screenwriter puts into a script when the plot requires something that physics does not actually permit. Energy below zero, less than nothing. It sounds meaningless. It is not meaningless. It is real, and we have experimental proof of its existence. The proof comes from a phenomenon called the Casimir effect, predicted theoretically by Dutch physicist Hendrik Casimir in 1948. And first measured experimentally in 1958, with increasingly precise measurements conducted through the following decades. Here is the setup. Take 2 flat, uncharged metal plates, place them in a perfect vacuum, parallel to each other, separated by an extremely small distance, on the order of micrometers, millionths of a meter. There are no electrical charges on the plates. There is no magnetic field. There is no air between them. No fluid, no medium of any kind, nothing. And yet the plates are pushed together by a force that should not be there. The explanation requires quantum mechanics, specifically the quantum mechanical description of empty space. In quantum field theory, the vacuum, the state of lowest possible energy, is not actually empty. It is a seething, roiling foam of what physicists call virtual particles, pairs of particles and antiparticles, electrons and positrons, quarks and antiquarks, photons materializing from nothing, existing for an instant too brief to measure directly, and then annihilating each other and returning to nothing. This sounds impossible. Matter appearing from nothing, from empty space, from pure vacuum, but it is a direct and unavoidable consequence of the Heisenberg uncertainty principle. The uncertainty principle states that there is a fundamental limit to how precisely you can simultaneously know the energy of a system and how long that energy exists. Over sufficiently short time intervals, energy can fluctuate wildly without violating any conservation law. As long as the fluctuation is brief enough, particles borrow energy from the vacuum, exist for the permitted instant, and repay the debt by annihilating. The vacuum is never truly empty. It is always doing something. It has what physicists call zero-point energy, the irreducible minimum energy of a quantum field, even at absolute zero temperature, even in the complete absence of any particles. Now, here is the crucial part. When you place 2 metal plates close together, you impose a constraint on the virtual particles that can exist in the space between them. The plates are boundaries. Only virtual particles whose wavelengths fit exactly between the plates. the way a guitar string can only vibrate at wavelengths that fit between its two fixed endpoints, are permitted to exist in that space. Virtual particles with other wavelengths are excluded. Outside the plates, in the open space beyond, no such constraint exists. Every wavelength is permitted. Every virtual particle that quantum mechanics allows can appear and disappear freely. The result is an imbalance. There are more virtual particles, more quantum fluctuations, more zero-point energy pressing on the outer faces of the plates than on the inner faces. This creates a net inward force, a pressure pushing the plates together. The force is tiny, measured in nanonewtons for plates separated by micrometers, but it is real. It has been measured in laboratories many times. The measurements match the theoretical predictions with extraordinary precision, and the energy density in the space between the plates is negative. It is lower than the energy density of the vacuum outside the plates. You have created a region where the energy of space is below the baseline energy of empty space, below zero, negative. Negative energy exists, not in some theoretical, purely mathematical sense. It has been created in laboratories. It has been measured with instruments. It is a physical reality. The Alcubierre drive requires negative energy distributed throughout the warp bubble wall in specific geometric configurations and at specific densities. The Casimir effect demonstrates that negative energy can be created by constraining quantum vacuum fluctuations with physical boundaries. The problem is scale. The negative energy produced by the Casimir effect between laboratory plates is almost inconceivably small. The force between two plates, a micrometer apart and a centimeter square, is roughly 10 to the power of -8 newtons. The energy density is negative, yes, but it is negative by an amount that makes a single atom look enormous by comparison. We are talking about energy densities so small that they are only detectable with instruments of extraordinary sensitivity in environments of extreme isolation from any vibration or electromagnetic interference. To power even the most optimized version of an Alcubierre warp bubble, you would need negative energy densities millions or billions of times greater than anything the Casimir effect produces, distributed throughout a region of space potentially meters or tens of meters across, shaped with precise geometric accuracy and maintained stably for the duration of the journey. We have no idea how to do this. We do not even have a theoretical framework that tells us whether it is possible. We know negative energy exists in tiny amounts under specific conditions. We do not know whether it can be amplified, concentrated, or engineered at the scales and densities an Alcubierre drive would require. Some researchers have proposed using arrays of electromagnetic fields, standing waves of radiation configured in specific geometries, to enhance the Casimir effect and produce larger amounts of negative energy. Harold White at NASA EagleWorks conducted experiments with this in mind, attempting to detect any measurable space-time distortion produced by optimized Casimir-like configurations. The results were inconclusive. No detectable warp effect was observed, though the experiment was operating at energy densities many orders of magnitude below anything that could be expected to produce a measurable result. The experiment was not a failure. It was an exploration, a probe of territory that had not been explored before, but it was also a reminder of how enormous the gap is between what the mathematics describes and what our current technology can approach. The distance between knowing that negative energy exists and knowing how to produce it in the quantities and configurations an Alcubierre drive requires is not a gap that engineering alone can close. It may require new physics, new understanding of how quantum fields behave under extreme conditions, new theoretical frameworks that we do not yet possess. And even if all of these problems were solved, even if some future civilization found a way to generate negative energy at the required densities and configure it into a stable warp bubble, there would still remain the deepest problem of all, the one that is not about energy or engineering or exotic matter, the one that is about the structure of time itself. There is a question that physicists ask about any proposed mechanism for faster-than-light travel, and it is not the question you might expect. It is not how much energy would this require, though that matters enormously. It is not what exotic materials would be needed, though that matters too. The first question, the one that cuts deepest, the one that reaches down into the foundations of logic itself, is this. If this works, can you use it to go back in time? Because if the answer is yes, then the universe may not simply make the mechanism difficult to achieve. It may forbid it entirely, through consequences so catastrophic for the structure of causality, for the basic logical framework of cause preceding effect, that the universe's own internal consistency demands its impossibility. This connection between faster-than-light travel and time travel is not obvious at first. They seem like separate ideas. Moving very fast through space is one thing, moving backward through time is another. But they are not separate. Under the mathematics of special relativity, they are deeply, inescapably linked. And understanding why requires confronting one of the strangest and most counterintuitive features of Einstein's universe. There is no universal now. This is not a philosophical statement. It is a precise, experimentally confirmed mathematical fact about the structure of space-time. There is no moment that is simultaneously now for all observers everywhere in the universe. Different observers moving at different velocities disagree about which events are happening at the same time. What is simultaneous from your perspective is not simultaneous from the perspective of someone moving relative to you, and both of you are correct. There is no fact of the matter about which set of simultaneous events is the real one. This is called the relativity of simultaneity, and it has been confirmed by every precision test of special relativity ever conducted. Here is a thought experiment to make it concrete. Imagine a train car moving along a track at high speed. A lightning bolt strikes each end of the car simultaneously from the perspective of someone standing beside the track, watching the train pass. The two flashes happen at the same moment. The observer beside the track sees both flashes reach the midpoint of the car at the same time, confirming they were simultaneous. Now consider the perspective of a passenger sitting at the midpoint of the train car. From their perspective, the train is stationary and the track is moving. The flash from the front of the car, in the direction the car is moving relative to the track, reaches the passenger first, because the passenger is moving toward the front flash and away from the rear flash. The front flash was therefore closer when it happened, from the passenger's perspective, which means it happened earlier. The two flashes were not simultaneous from the passenger's perspective. The front one happened first. Both observers are correct. There is no single objective truth about whether the flashes were simultaneous. Simultaneity is relative to the observer's frame of motion. Two events that are simultaneous in one reference frame are not simultaneous in another reference frame, moving relative to the first. At everyday speeds, this effect is too small to notice. The difference in simultaneity between a person sitting on a bench and a person driving past in a car is measured in fractions of a nanosecond across distances of meters. But as velocities increase toward the speed of light, the effect becomes dramatic. Two observers moving at a significant fraction of light speed relative to each other can disagree about the timing of distant events by years or decades or centuries, depending on the distance involved. Now, introduce faster-than-light travel. Imagine you have a spacecraft equipped with an Alcubierre drive. You depart from Earth in the year 2200 by Earth's calendar and travel to a star system 10 light-years away at 10 times the speed of light. By your own measurement, the journey takes roughly 1 year. You arrive in the year 2201 by your reckoning. From the perspective of someone on Earth watching you depart and arrive, the journey also appears to take about 1 year, since the warp bubble carries you through 10 light-years of distance in roughly 1 year of Earth time. You left in 2200 and arrived in 2201. Simple, linear, causal. Now, you decide to return to Earth. You activate your warp drive again and make the return journey at the same speed. From your perspective, another year passes. You arrive back at Earth in 2202 by your reckoning. This seems entirely consistent. You spent 2 years traveling, 1 year out and 1 year back, and you arrived 2 years after you left. No paradox, no problem. But now consider the perspective of an observer who is moving relative to Earth at a significant fraction of the speed of light. Due to the relativity of simultaneity, this observer's definition of now is tilted relative to yours. Events that you consider to be in the future are, from this observer's perspective, already in the past or happening right now. For a sufficiently fast-moving observer at the right velocity, your arrival at the distant star system, which you consider to happen in 2201, is simultaneous with events on Earth that happened in 2199. From this observer's tilted perspective of now, you arrived at your destination before you left. Not by much, not by years or centuries, but the order is reversed. Effect precedes cause. If you then make your return journey from this reference frame, you can, under specific conditions that the mathematics of special relativity makes precise, arrive back at Earth at a moment that, in Earth's calendar, is before you originally departed. You left in 2200. You arrive back in 2199. You could shake hands with yourself before you left. You could tell yourself not to go. You could prevent the journey that led to your return. And if you prevent the journey, you never return to warn yourself. So you do go, so you do return, so you do warn yourself, so you do not go, so you do return. This is the grandfather paradox, the oldest and most familiar time travel paradox, dressed in the mathematics of special relativity and faster-than-light travel. And it is not a philosophical puzzle or a science fiction scenario. It is a direct mathematical consequence of combining superluminal motion with the relativity of simultaneity. Any mechanism for faster-than-light travel, regardless of the physical details, can in principle be used from the right reference frame to send information or matter backward in time. The Alcubierre drive is no exception. Physicists examined this carefully in the years following Alcubierre's 1994 paper. The conclusion was unavoidable. A sufficiently advanced civilization with access to 2 Alcubierre drives could, by making 2 faster-than-light journeys in carefully chosen directions from carefully chosen reference frames, construct what mathematicians call a closed time-like curve, a path through space-time that loops back to its own past, a path along which you could travel and arrive at the point in time from which you departed. A time machine, not a metaphorical time machine, not a narrative convenience, a literal, physically realizable, mathematically rigorous closed time-like curve permitted by the same general relativity that makes the Alcubierre metric a valid solution to Einstein's equations. This was deeply troubling to physicists, not because time travel is an exciting prospect, but because time travel into the past creates logical contradictions that the universe, as far as we can tell, is not supposed to contain. The universe appears to be logically consistent. Causes precede effects. Events follow from prior events in a coherent chain. The past is fixed, and the future is open. These are not merely conventions or assumptions. They are features of every physical theory we have ever developed, confirmed by every observation we have ever made. Closed time-like curves destroy this. They create situations where an effect can precede its own cause, where the existence of a sequence of events depends on the non-existence of that same sequence of events, where the logical structure of the universe folds back on itself and generates contradictions that have no resolution. And most physicists believe the universe does not permit this. In 1992, Stephen Hawking proposed what he called the chronology protection conjecture. It is not a theorem, it is not a law in the formal sense. It is a conjecture, an educated hypothesis based on the observed behavior of physics in extreme conditions. The conjecture states, simply, that the laws of physics conspire to prevent the formation of closed time-like curves, that whenever a physical process threatens to create a time machine, something goes wrong, some barrier arises, some pathology develops in the mathematics that prevents the time machine from forming. Hawking called this chronology protection because the universe appears to protect the chronological ordering of events. Causes before effects, always, without exception. The universe, in Hawking's formulation, is its own timekeeper, and it enforces the rules. The evidence for this conjecture is suggestive, though not conclusive. Every time physicists have constructed a theoretical model that appears to allow time travel, something has gone wrong in the mathematics. Energy requirements diverge to infinity at precisely the moment when the time machine would become operational. Quantum effects destabilize the very space-time configurations that would allow closed time-like curves to form. Virtual particles pile up in feedback loops that produce infinite energy densities, destroying the structure before it can be used. It is as though the universe detects the threat and responds, as though every route to time travel is guarded not by a single wall but by multiple walls, each one appearing exactly when and where it is needed to block the passage. The barriers are not the same barrier. They arise from different areas of physics, quantum mechanics, thermodynamics, the behavior of quantum fields in curved space-time, but they all arrive at the same destination. They all say no. This pattern is so consistent that many physicists treat the chronology protection conjecture not as a guess, but as something close to a law, a feature of reality that deeper theories will eventually explain from first principles, but which can already be observed in the behavior of the theories we have. Hawking himself noted in later work that the conjecture, if true, would have a silver lining. It would make the universe safe for historians. What this means for the Alcubierre drive is sobering. Even setting aside the energy requirements, even imagining that some future civilization could generate the required negative energy at the required densities in the required configurations, the warp drive might be prohibited not by the difficulty of its construction, but by what it would make possible once built. If any faster-than-light travel mechanism allows the construction of a time machine, and the mathematics of special relativity says it does, then the chronology protection conjecture says the universe will not allow it to function. The mechanism by which this prevention occurs in the specific case of the Alcubierre drive is not fully understood. Physicists have shown that quantum vacuum fluctuations, the same virtual particles that produce the Casimir effect, behave strangely in the vicinity of a warp bubble. They pile up at the walls of the bubble. They build in intensity as the bubble approaches the speed of light. Some calculations suggest that this build-up produces an energy density at the bubble wall that grows without bound as the bubble accelerates, potentially destroying the bubble from the inside before it can reach superluminal speeds. This would be the universe enforcing its own speed limit through a quantum mechanical mechanism rather than a relativistic one, not saying you cannot have infinite energy, but saying that the very act of trying to create a warp bubble generates a quantum feedback loop that tears the bubble apart before it becomes dangerous. These calculations are incomplete. We do not have a full theory of quantum gravity, the framework that would let us calculate what happens when both quantum effects and gravitational effects are important simultaneously. The behavior of quantum fields in the curved space-time of an Alcubierre bubble has been studied only partially, with tools that physicists acknowledge are insufficient for the full problem. The calculations that suggest the bubble would be destroyed are suggestive, not definitive, but the direction they point is consistent. Every investigation of the detailed physics of the Alcubierre drive finds new problems. Every attempt to make it work runs into new barriers. And those barriers are not random. They cluster around the same issue. The warp drive, if it worked, would make time travel possible. The universe appears to be structured in a way that prevents this. And one way the universe might prevent it is by ensuring that the warp drive itself cannot work. There is something almost philosophical about this. The universe does not seem to forbid faster-than-light travel through a single, simple, obvious prohibition. Instead, it sets up a chain of consequences. If you travel faster than light, you can build a time machine. If you can build a time machine, you can create causality violations. If causality is violated, the logical structure of reality breaks down, and reality, apparently, does not allow its own logical structure to break down. So the entire chain is forbidden, beginning with the first link. The prohibition on faster-than-light travel is not the law itself. It is the consequence of a deeper law, the law that says causes must precede effects, that the universe must be internally consistent, that logic cannot be violated. Whether this deeper law is truly absolute, whether there is some exotic configuration of space-time or some feature of quantum gravity, we have not yet discovered that threads the needle between faster-than-light travel and causality violation. Remaining faster than light, while somehow avoiding closed time-like curves, is not known. Some physicists have speculated about this. There are theoretical proposals suggesting that certain kinds of warp metrics might avoid creating time machines under certain conditions, but none of these proposals have been fully worked out. None of them have been shown to be free of all the problems that plague the original Alcubierre metric. The deeper you look, the more the barriers reinforce each other. Energy requirements that might be impossible, exotic matter that barely exists, quantum instabilities that may destroy the bubble in formation. And underlying all of it, the suspicion, supported by increasingly careful mathematics, that the universe has decided this particular door should remain closed. And yet, the universe has surprised us before. The barriers we thought were fundamental have sometimes turned out to be provisional. The laws we thought were absolute have sometimes turned out to be approximations, correct within their domain but incomplete at the edges. And at the edges of our current understanding, at the point where quantum mechanics and gravity meet and our theories break down and give nonsensical answers, there may be something we are missing, something that changes the picture in ways we cannot yet foresee. We do not know. That is the honest position. We do not know whether the barriers to faster-than-light travel are truly fundamental, or whether they are artifacts of our current incomplete theories. We do not know whether the chronology protection conjecture is a real law of nature, or a pattern that breaks down when examined with better tools. We do not know whether the universe's apparent determination to prevent time travel reflects something deep and absolute or something contingent, a feature of the physics we know rather than the physics that exists. What we can say is this: every path we have found toward faster-than-light travel leads, eventually, to the same precipice, the edge where causality wavers, where the logical structure of time begins to bend back on itself, where the universe seems to look at what we are building and decide, through whatever mechanism it uses for such decisions, that this is far enough. Not yet, perhaps not ever, but there are other doors, other theoretical approaches that do not rely on the Alcubierre metric, that approach the problem from different directions, that offer different possibilities and different problems. And examining them tells us something important, not just about whether faster-than-light travel is possible, but about the shape of our ignorance, about where the boundaries of our knowledge actually lie, and what might be waiting on the other side. The Einstein-Rosen bridge was not discovered by anyone looking for a shortcut through space. It was discovered by two men trying to understand something else entirely, trying to make sense of a solution to general relativity that seemed to describe something impossible, and finding in the process a mathematical structure so strange that it took decades for anyone to understand what it actually was. In 1916, a German physicist named Karl Schwarzschild was serving on the Eastern Front of the First World War. He was doing artillery calculations, performing the grim mathematics of trajectories and ballistics, and somehow, in whatever hours remained after the work of war was done, he was also solving Einstein's field equations. Einstein had published his general theory of relativity just months earlier, in November 1915, and Schwarzschild was among the first to find an exact solution to the equations for a specific physical situation: a perfectly spherical, non-rotating mass sitting alone in otherwise empty space. He sent his solution to Einstein in a letter from the trenches. Einstein was astonished. He had not expected an exact solution to be found so quickly. The equations were formidably complex, and most physicists assumed that only approximate solutions, valid under specific limiting conditions, would be achievable in practice. Schwarzschild's solution was exact, and it contained something troubling. At a specific distance from the center of the mass, a distance now called the Schwarzschild radius, the mathematics behaved strangely. Certain quantities in the solution became infinite. The equations seemed to break down. At the time, most physicists assumed this was a mathematical artifact, a sign that the solution ceased to be physically meaningful at that point, that nothing real could actually compress to within its own Schwarzschild radius. They were wrong about that. What Schwarzschild had found was the mathematical description of a black hole, though that term would not be coined for another half-century. The Schwarzschild radius defines the event horizon, the boundary within which escape from the gravitational field becomes impossible. Karl Schwarzschild died of a disease contracted at the front just months after sending his letter to Einstein. He never knew what he had found. 19 years later, in 1935, Einstein himself working with a younger physicist named Nathan Rosen at the Institute for Advanced Study in Princeton, was examining the Schwarzschild solution more carefully. They found something the original derivation had not made clear. The solution described not one region of spacetime but two. The equations were symmetric. There was a black hole, a region from which nothing could escape, and there was, mathematically speaking, a mirror image on the other side, a region that nothing could enter from the outside, which physicists would later call a white hole. And connecting these two regions, buried in the mathematics of the Schwarzschild solution, was a throat, a narrow passage linking the two regions of spacetime. Einstein and Rosen called this structure a bridge. It is now called an Einstein-Rosen bridge, or, in the language that physicist John Wheeler, the name wormhole comes from an analogy. Imagine an apple. A worm on the surface of the apple, traveling from one side to the other, must crawl along the curved surface, following the contour of the fruit. But a worm that burrows through the apple can travel a much shorter distance in a straight line through the interior. The surface distance between 2 points on a sphere can be far greater than the distance through the interior. A wormhole in space-time is the cosmic equivalent of the worm's tunnel, a passage through the interior of space-time's geometry, connecting 2 points that might be enormously distant if you had to travel along the surface. The mathematics was clear. The Schwarzschild solution contained this structure. It was not invented or hypothesized. It was there, in the equations, from the beginning. Einstein and Rosen had simply made it explicit. But there was an immediate problem. The Einstein-Rosen bridge, as described by the original Schwarzschild solution, is not traversable. It is not a tunnel you could enter at one end and emerge from at the other. The throat of the bridge is unstable, in a way that makes transit impossible. It forms and collapses faster than light can cross it. Even if you entered at one end moving at the speed of light, the bridge would pinch shut before you reached the other side. You would not emerge in another region of space-time. You would be destroyed by the collapsing geometry. The wormhole existed, but it was useless. A tunnel that closes before you can walk through it. For decades, this was the state of the theory. Wormholes were mathematically real, but physically inaccessible. A curiosity in the equations, not a viable mechanism for travel. Then, in 1988, physicists Kip Thorne and Mike Morris at Caltech, working in part at the request of Carl Sagan, who wanted to know whether wormholes could be made traversable for a novel he was writing, what would become the book Contact, published a paper that changed the conversation. Thorne and Morris asked a simple question. What would it take to make a wormhole traversable? What conditions would have to be satisfied, mathematically and physically, for a wormhole to remain open long enough for a traveler to pass through? Their analysis was careful and systematic. They worked out the conditions that a traversable wormhole's geometry would have to satisfy. The throat would have to be wide enough to allow passage. The tidal forces, the stretching and compressing forces produced by differences in gravitational strength across the traveler's body, would have to remain below lethal levels. The wormhole would have to remain stable for the duration of transit. And what they found was that satisfying these conditions required the same ingredient that the Alcubierre drive required: negative energy. Matter or fields with negative energy density distributed throughout the throat of the wormhole to prevent it from collapsing, to hold the tunnel open against the gravitational pressure that would otherwise pinch it shut. The same exotic ingredient, the same substance that the Casimir effect demonstrates, can exist in principle, but only in quantities so small they make dust look substantial. To hold open a wormhole large enough for a human body, let alone a spacecraft, you would need negative energy distributed throughout the throat in amounts that dwarf anything the Casimir effect produces by many orders of magnitude. Some calculations suggest that holding open a wormhole 1 meter across would require negative energy equivalent to the mass energy of Jupiter, concentrated in the throat. Other calculations suggest even larger requirements. The numbers vary depending on the specific geometry of the wormhole and the assumptions made about the matter distribution, but they are all large, and they are all negative. We are back to the same war. Negative energy exists. We know how to make it in the laboratory. In amounts so small, they require the most sensitive instruments in the world to detect. Making it in the quantities needed to stabilize a wormhole is beyond anything we currently understand how to do, or even whether it is physically possible to do. And there is a second problem with wormholes, one that is distinct from the energy requirements, a problem of geometry and logistics that does not depend on exotic matter at all. A wormhole connects two mouths, two openings in space-time, one here and one there. To use a wormhole to travel from Earth to a distant star, you need one mouth located at Earth and one mouth located at the destination. But how do you get the second mouth to the destination in the first place? You cannot simply open a wormhole in space and specify where the other end appears. The mathematics does not work that way. Both mouths are physical objects, regions of highly curved space-time that exist at specific locations. To place one mouth at a distant star, you have to transport it there. And transporting it there, assuming you could somehow create and stabilize a wormhole mouth in the first place, which we have no idea how to do, would require moving it across the distance between Earth and the destination star, which means you have to cross that distance first, by conventional means, before you can use the wormhole for fast travel. You would spend thousands or millions of years transporting one mouth of the wormhole to its destination at sublight speeds. Only after completing that journey could you use the wormhole for instantaneous travel between the 2 points. The wormhole solves the problem of future travel once it is in place. It does nothing to solve the problem of the initial journey required to place it, unless wormholes already exist naturally. Unless the universe, in some regions we have not yet examined, contains wormholes formed by processes we do not yet understand, perhaps in the extreme conditions of the early universe, perhaps in the vicinity of black holes, perhaps as a feature of the quantum structure of space-time at the smallest scales. This possibility cannot be ruled out. We have not surveyed the entire universe. We have not examined the space-time in the vicinity of every black hole with sufficient precision to rule out connected structures. There are theoretical proposals suggesting that pairs of black holes that are quantum mechanically entangled, a phenomenon called ER equals EPR, after a 2013 paper by Juan Maldacena and Leonard Susskind, might be connected by microscopic wormholes. If this connection is real, and if it could be engineered and enlarged, it might provide a route to traversable wormholes that does not require transporting a mouth across interstellar distances. But this is deeply speculative. The ER equals EPR proposal is a theoretical conjecture about the relationship between space-time geometry and quantum entanglement. It is not established physics. It has not been tested. It opens as many questions as it answers. And wormholes, like the Alcubierre drive, run into the same causality problem. Thorne himself recognized this. A traversable wormhole can be turned into a time machine through a relatively simple procedure. Take one mouth of the wormhole and accelerate it to near light speed for a period of time, then bring it back. Due to relativistic time dilation, the accelerated mouth ages less than the stationary mouth. A time difference develops between the two ends. Step through the wormhole from the younger mouth to the older mouth, and you travel forward in time. Step through from the older mouth to the younger mouth, and you travel backward in time. Again, chronology protection. Again, the same barrier. Again, the universe looking at what is being built, and, through whatever quantum mechanisms it employs, apparently deciding that this is not permitted. Quantum entanglement offers a different kind of hope, or seems to, until you look at it carefully. It is perhaps the most misunderstood phenomenon in all of physics, simultaneously the most genuinely strange thing we have confirmed about the universe, and the least useful for the purpose people most want to use it for. Two particles that have interacted in the right way become entangled. Their quantum states become correlated in a way that persists regardless of the distance between them. Measure a property of one particle and you instantly know the corresponding property of the other, even if it is on the other side of the galaxy. The measurement of one particle appears to instantly influence the state of the other. Not influence it by sending a signal. Influence it directly, non-locally, without any time delay for the information to travel. Einstein called this spooky action at a distance, and he spent the rest of his life trying to convince himself and others that it could not actually be happening, that there must be some deeper explanation, some hidden variables, some information carried by the particles from the beginning that determined the outcome of both measurements before either one was made. He was wrong. In 1964, physicist John Bell derived a set of mathematical inequalities that any hidden variable theory, any theory in which the correlations were explained by prior shared information, must satisfy. In the early 1980s, physicist Alan Aspect conducted experiments that tested these inequalities with entangled photons. The inequalities were violated. Hidden variables, at least of the local variety Einstein had in mind, do not exist. The correlations are real. They are instantaneous. They are not explained by any information the particles carried from the beginning. This has been confirmed with increasing precision in experiments across the following 4 decades. China's Messius satellite, launched in 2016, demonstrated entanglement between particles separated by more than 1,200 kilometers. The correlations were instantaneous to within the measurement precision of the experiment. There was no detectable time lag corresponding to any signal traveling between the particles. So something is happening faster than light. The question is whether that something carries information. It does not. This is the crucial point that is so often missed in popular discussions of entanglement. The instantaneous correlation between entangled particles cannot be used to transmit information, and the reason is not technological. It is not that we lack the clever devices needed to extract information from the correlations. It is fundamental, mathematical, built into the structure of quantum mechanics at a level that cannot be circumvented by any clever engineering. Here is why. When you measure an entangled particle, you get a random result. If you are measuring the spin of a particle, you get spin up or spin down, and quantum mechanics tells you the probability of each outcome, but the actual result is fundamentally random. You cannot control or predict or influence which outcome you get. The randomness is not ignorance. It is not a limitation of your measuring equipment. It is the actual nature of the quantum measurement process. Now, the moment you measure your particle and get, say, spin up, you know that your distant partner's particle, when measured, will give spin down. The correlation is perfect and instantaneous. But your partner, sitting at the other end of the universe, measures their particle and gets spin down. From their perspective, they got a random result. They do not know whether they got spin down because you measured spin up, or because their particle was always going to give spin down regardless of what happened to its entangled partner, or because of any other reason. To them, the result looks like a random outcome from a random process. They cannot tell the difference. The measurement outcome carries no information about what you did because the outcome is random. You cannot encode a message in a random result. To send information, you need to be able to choose what the recipient receives. Entanglement gives the recipient a random bit, not a bit you chose. The only way to demonstrate that the correlation is real, to show that your spin up is genuinely correlated with their spin down rather than being a coincidence, is to compare your results. And comparison requires communication. You have to call them or send them a message or wait for them to travel to you. And that communication travels at the speed of light or slower. The instantaneous correlation is real but invisible until you receive classical information confirming it, information that cannot travel faster than light. This is not a technicality. It is not a loophole waiting to be closed. It is a fundamental feature of quantum mechanics that physicists have examined exhaustively from every possible angle for decades and found to be inviolable. Quantum entanglement does not allow faster-than-light communication. Not now. Not with better technology. Not in principle. Quantum teleportation, a related phenomenon that has been demonstrated in laboratories and is sometimes cited in popular discussions as evidence that faster-than-light travel might be possible, does not change this conclusion. Quantum teleportation allows the quantum state of a particle to be transferred from one location to another, but it requires the transmission of classical information between sender and receiver to complete the transfer. Without that classical information, traveling at light speed, the recipient cannot reconstruct the teleported state. The quantum information arrives instantaneously in an encoded, inaccessible form and is unlocked only when the classical key arrives at light speed. Nothing, not even quantum information, is transmitted faster than light, there remains one more avenue worth considering, one that does not involve warping space-time or holding open wormholes or exploiting quantum correlations. It involves the possibility that space-time itself has more dimensions than the three of space and one of time that we experience directly. String theory, the leading candidate for a theory of quantum gravity, requires the existence of additional spatial dimensions beyond the three we can perceive. Depending on the version of the theory, there are 6 or 7 additional spatial dimensions, all of them compactified, curled up at each point in space into shapes so small, on the order of the Planck length, 10 to the power of -35 meters, that they have never been detected and cannot be detected with any currently conceivable instrument. If these extra dimensions exist, and we do not know that they do, then the three-dimensional space we inhabit is something like a surface, a membrane, a brain in the language of string theory, embedded in a higher dimensional space that physicists call the bulk. Our three dimensions are real and physical, but they are not all that exists. There is more to space than we can perceive. And if there is more to space than we can perceive, then the distances we measure between points in our three-dimensional space may not be the actual shortest distances between those points in the full higher dimensional reality. Return to the apple analogy. A worm confined to the surface of the apple must travel along the curved two-dimensional surface. The shortest path between 2 points on opposite sides of the apple, measured along the surface, is half the circumference, but through the interior, through the third dimension the worm cannot access, the shortest path is just the diameter. For a large apple, the surface distance might be 3 times the interior distance. If our three-dimensional space is like the surface of that apple, embedded in a higher dimensional bulk, then the actual shortest path between 2 points in our space might be far shorter than the three-dimensional surface distance suggests. A shortcut through the bulk, not a wormhole, not a warp bubble, but a path through dimensions we cannot normally access. A civilization that somehow developed the ability to leave the brain, to move through the bulk, could potentially cross distances that appear enormous from within three-dimensional space in a much shorter time by taking the straight line through the interior rather than the long, curved path along the surface. This is purely speculative. String theory is unproven. Extra dimensions have not been detected. We have no theoretical framework that tells us how matter or energy confined to a three-dimensional brain could ever escape into the bulk. Even if the extra dimensions exist, our particles, made of open strings in the language of string theory, are bound to the brain. Only gravitons, which correspond to closed strings, can propagate freely through the bulk. But as a mathematical possibility, as a feature of our current best candidate theory for quantum gravity, it cannot be dismissed. If extra dimensions exist, and if some mechanism could be found to use them as shortcuts, the three-dimensional distances between stars might be, in some physical sense, far smaller than they appear. The universe might be more connected, at a level we cannot yet perceive, than the vast emptiness we observe suggests. Every door opens onto another wall. Every theoretical route to faster-than-light travel leads to a place where our knowledge runs out and uncertainty begins. The Alcubierre drive is mathematically valid but physically problematic in ways that may be fundamental. Wormholes exist in the equations, but require exotic matter in quantities that may be impossible to produce and lead to time travel paradoxes that the universe appears to forbid. Quantum entanglement is real and instantaneous, but carries no information and allows no communication faster than light. Extra dimensions might provide shortcuts, but we cannot access them, do not know they exist in the form needed, and have no idea how to reach them even in theory. And yet, the universe still has secrets it has not revealed. Our theories are still incomplete. There are still questions we cannot answer, and regions of physics we cannot reach. And in those gaps, in those places where our knowledge gives out and the equations break down and the answers become infinite or undefined, something might be hiding, something that changes everything. In 1950, a group of physicists were walking to lunch at the Los Alamos National Laboratory in New Mexico. The conversation had turned, as it sometimes did among people who spent their days thinking about the deepest questions in science, to the subject of extraterrestrial life. There had been a cartoon in a New Yorker magazine that week, depicting flying saucers and little green men, and the topic was in the air. The physicists were joking about it, speculating loosely about whether interstellar travel was possible, whether alien civilizations existed, whether the universe was populated with other minds looking up at the same stars. And then, one of the men at the table, a physicist named Enrico Fermi, one of the architects of the first nuclear reactor and one of the most penetrating minds in the history of physics, went quiet for a moment. And then he asked a question: "Where is everybody?" The table fell silent. The other physicists understood immediately what he meant, not as a joke, not as a casual aside, as a genuine scientific puzzle, a contradiction between what the logic of probability seemed to demand and what observation actually revealed. The question has haunted science ever since. The logic is straightforward, and its conclusion seems almost inescapable. The Milky Way galaxy is approximately 13.6 billion years old. It contains somewhere between 200 billion and 400 billion stars. We now know, from the Kepler Space Telescope and its successor TESS, that planets are not rare exceptions but the rule. Most stars have them. Many stars have multiple planets. Estimates based on Kepler's data suggest there are at least 1 billion Earth-sized planets in the habitable zones of their stars in our galaxy alone. 1 billion worlds where liquid water could exist on the surface, where the chemistry of life, as we understand it, could potentially operate. On Earth, life appeared remarkably quickly after the planet became habitable. Earth formed approximately 4 billion years ago. For the first several hundred million years, it was a hellish environment, bombarded by asteroids, its surface partially molten, its atmosphere unbreathable by any standard of complexity. But by approximately 3.8 billion years ago, possibly earlier, living organisms had already appeared. Life did not wait. It did not require billions of years of preparation or the occurrence of some extraordinary improbable event. It emerged as soon as conditions permitted, within what is, on geological and cosmic timescales, essentially no time at all. This suggests that life, at least simple microbial life, may be easy to start. Given the right ingredients, liquid water and organic molecules and energy sources, which are common throughout the universe, life appears to find a way. If this is true, then a significant fraction of those billion habitable worlds in the Milky Way might harbor life. And if life is common, intelligence is at least possible. It took approximately 3.5 billion years for Earth to go from the first simple cells to a species that could build radio telescopes and particle accelerators and launch probes to the edge of the solar system. That is a long time, but the galaxy is 13.6 billion years old. There was time. There was more than enough time. Stars like our Sun formed in the Milky Way as long as 10 billion years ago. Planets could have formed around those stars 9 or 10 billion years ago. Life could have started 8 or 9 billion years ago. Intelligence could have emerged billions of years before the first human being drew breath on this planet. A civilization that arose just 1 million years before humanity would have a 1 million year head start in technology. 1 million years ago, our ancestors were making simple stone tools, hunting with handcrafted spears, living in small bands that had no conception of what a star actually was. In 1 million years, we went from stone tools to spacecraft, from cave paintings to the Large Hadron Collider, from a species that could not cross an ocean to a species that has left its solar system. Voyager 1, launched in 1977, is currently more than 23 billion kilometers from Earth, traveling through interstellar space, the first human-made object to do so. What could a civilization 1 million years more advanced than us achieve? What could a civilization 1 billion years more advanced achieve? Even without faster-than-light travel, the problem persists. At 10% of the speed of light, a speed that is extraordinarily fast by our current standards but not obviously impossible for a civilization of sufficient technological maturity, a spacecraft could cross the Milky Way in 1 million years. The galaxy is 100,000 light-years across. At 10% light speed, the crossing takes 1 million years. That sounds enormous, but it is less than 1/10 of 1% of the galaxy's age. Self-replicating probes, machines that travel to a star system, use the resources they find there to build copies of themselves and send those copies onward, could fill the entire galaxy exponentially. Starting from a single origin point, each probe building two more, each of those building two more. The process would cover every star system in the Milky Way in a cosmologically brief period of time. Estimates suggest that even accounting for travel time and construction time, self-replicating probes could explore or colonize the entire galaxy in somewhere between 1 million and 10 million years. 10 million years is nothing in the context of a 13.6 billion-year-old galaxy. It is less than 0.1% of the galaxy's age. If even one civilization had arisen even 10 million years ago and begun this process, the probes should be everywhere by now. Every star system should have been visited. Every habitable world should have been examined. Earth should have received visitors long ago, or at minimum, should show clear evidence of having been examined by an alien probe at some point in its 4.5 billion-year history. And we have nothing. No probes, no signals, no artifacts, no structures, no evidence of any kind that any intelligence other than our own has ever been present in this solar system or has ever directed communication toward this planet. The search for extraterrestrial intelligence, SETI, has been listening for radio signals from other civilizations since 1960. In more than 6 decades of listening, scanning thousands of stars across multiple frequency bands, searching for the narrowband signals that only technology produces, the result has been silence. Not suggestive silence, not a silence interrupted by occasional hints. Silence, that is, with one possible exception we will return to in a moment, completely unbroken. We have looked for laser pulses, brief optical flashes that an advanced civilization might use for interstellar communication. Nothing. We have searched for evidence of megastructures, Dyson spheres or partial Dyson swarms built around stars to harvest their energy, which would produce distinctive infrared signatures detectable from Earth. Several interesting candidates have been identified. Stars with unusual dimming patterns or unexpected infrared excess, but none have withstood careful scrutiny as evidence of technology. The explanations have been natural in every case. We have examined the atmospheres of exoplanets, looking for the chemical signatures of industrial activity, for compounds that have no natural source and could only be produced by technology. We have found nothing conclusive. The one possible exception is the WOW signal, detected on the 15th of August 1977 by astronomer Jerry Ehman using the Big Ear radio telescope at Ohio State University. Ehman was reviewing a printout of radio telescope data and found a signal so strong, so precisely what a transmission from an extraterrestrial civilization might look like, that he circled it on the printout and wrote the word WOW in the margin. The signal lasted 72 seconds, the maximum duration the Big Ear telescope could observe any given point in the sky as Earth rotated. It appeared to come from the direction of the constellation Sagittarius. It was at a frequency close to the 1,420 MHz frequency of neutral hydrogen, the most common element in the universe, and therefore the frequency that some theorists have suggested an intelligent civilization might use for interstellar broadcasts. The WOW signal has never been explained. It has also never been detected again. Dozens of subsequent observations of the same region of sky with the same and better instruments have found nothing. A signal that appears once and never repeats provides very little basis for any conclusion. It might have been a brief natural phenomenon, a comet outgassing producing an unusual radio emission, as was proposed in 2017. It might have been terrestrial interference. It might have been something else entirely. It might have been what Ehman thought it was. We do not know. And not knowing, having one anomaly in 6 decades of listening, is itself a kind of data. It says the universe is not broadcasting loudly and continuously on frequencies we can easily detect. Whatever is out there, if anything, is not making itself obvious. This is the Fermi paradox in its full weight. The universe is old, planets are common, life appears easy to start, intelligence appears to be a possible destination for evolution. The galaxy has had billions of years for civilizations to arise, expand, and make their presence known, and yet the sky is silent. There are many proposed solutions. They range from the deeply pessimistic to the quietly hopeful, and none of them is entirely satisfying. Perhaps life is not easy to start. Perhaps Earth's emergence of life was extraordinarily improbable, a fluke so unlikely that it has happened only once, or only a handful of times in the entire observable universe. Perhaps the ingredients are common, but the spark, whatever process converts chemistry into biology, is vanishingly rare. This is called the rare Earth hypothesis. It is possible, but it sits uncomfortably with how quickly life appeared on Earth, once conditions were right. Rare events do not typically occur as quickly as possible once the preconditions are met. Perhaps intelligence is rare. Perhaps the step from simple life to complex, technological intelligence is far harder than Earth's history suggests. Perhaps the 3.5 billion years from first cells to first telescopes is not a universal timeline but a minimum, and most planets with life never make the leap to intelligence in the time available before their star changes or some catastrophe intervenes. Perhaps we are one of the very first intelligent civilizations to arise in the Milky Way, simply because evolution is slow and the galaxy has not yet had enough time to produce many others. Perhaps civilizations destroy themselves. Perhaps every technological civilization eventually develops weapons or technologies powerful enough to annihilate itself, and eventually, inevitably, does so. Nuclear weapons, engineered pathogens, artificial intelligence systems that pursue goals incompatible with their creators' survival. Perhaps the window between developing radio telescopes and achieving self-destruction is measured in centuries rather than millennia, and we are simply in that window right now, too early to have been detected by others who preceded us, and too late to hear from the ones who came after. This is called the Great Filter, a term coined by economist Robin Hanson. The filter is whatever process, or combination of processes, eliminates civilizations before they become galaxy-spanning. If the filter is behind us, in our past, if the rare and difficult step was the emergence of life or the development of intelligence, then we are survivors, and the galaxy is largely empty because few others made it through. If the filter is ahead of us, if civilizations routinely destroy themselves at roughly our current level of development, then our silence is a preview, a warning of what is coming for us. Perhaps they are hiding. Perhaps advanced civilizations exist but choose not to be detected. The Dark Forest Hypothesis, elaborated by Chinese science fiction author Liu Cixin in a framework rooted in game theory, suggests that the universe might be a place where revealing your existence is dangerous, where any civilization that announces itself risks destruction by others who cannot afford to allow the existence of potentially threatening competitors. In this scenario, the silence is not absence, but concealment. Every civilization in the galaxy is listening and hiding, never transmitting, never exploring visibly, maintaining silence as the only rational survival strategy. This hypothesis has a certain dark logic to it, but it requires every civilization in the galaxy to independently arrive at the same conclusion and to maintain perfect radio silence indefinitely. It only takes one civilization to be noisy, curious, or indifferent to self-preservation for the hypothesis to fail, and Earth itself has been broadcasting radio signals into space for over a century. We have not been silent. Perhaps they exist, but communication is simply harder than we imagine. Perhaps the universe is full of civilizations that never develop radio telescopes, that evolve different senses and different technologies, that communicate through means we cannot detect or have not thought to look for. Perhaps the search for radio signals is like searching for telephone poles on an alien world as evidence of civilization, overlooking that they might have developed wireless communication 1,000 years before us and never strung a wire in their history. But here is the possibility that connects most directly to everything we have been examining tonight. The possibility that returns us to the question of the speed of light and what it means for the universe we inhabit. Perhaps faster than light travel is impossible. Truly, fundamentally, absolutely impossible. And that impossibility is the answer to Fermi's question. Think about what the Fermi paradox assumes. It assumes that a sufficiently advanced civilization could colonize the galaxy in a cosmologically brief period of time. The calculations that lead to this conclusion, the ones that say self-replicating probes could cover the Milky Way in 10 million years, assume travel at some fraction of the speed of light, 10%, 20%, perhaps higher for very advanced civilizations. These speeds are fast enough to make galaxy-wide expansion a manageable project on cosmic timescales. But what if no civilization, no matter how advanced, can travel faster than a few percent of light speed with any practical spacecraft carrying any significant payload? What if the energy requirements of near light speed travel are so enormous that they remain effectively impossible even for civilizations billions of years more advanced than us? What if the galaxy is not a place that can be colonized at all, but a collection of isolated systems, each trapped within its own tiny region of space, capable of reaching perhaps the nearest few dozen stars over thousands of years of effort but unable to spread further? In that universe, the silence makes sense, not because civilizations are rare, not because they destroy themselves, not because they are hiding, but because they cannot reach each other. Each civilization is an island separated from every other island by oceans so vast that no ship can cross them. They can look out across the water. They can see the lights of other islands on the horizon. They can send radio messages that take years or centuries or millennia to arrive. But they cannot visit. They cannot travel. They cannot meet. The galaxy would be full of life and full of intelligence and full of civilizations, each one looking up at the same stars we look at, asking the same question Fermi asked, hearing the same silence we hear, and drawing the same lonely conclusion that they are alone, not because nothing else exists, but because nothing else is reachable. This is perhaps the most unsettling resolution to the Fermi paradox, not because it requires rare events or catastrophes or conspiracies of silence, but because it requires only one thing, the thing we have been examining all night, the absolute, unbreakable, universe-wide speed limit, the law written into the fabric of space-time that says nothing moves faster than 186,282 miles per second, and that the distances between stars are therefore so large that they constitute an effective imprisonment for any civilization that arises within them. If this is true, then the universe is full of minds that will never meet, full of questions that will never be answered by collaboration between worlds, full of discoveries made in isolation, each civilization reinventing the same mathematics, the same physics, the same biology, never knowing that 1,000 other civilizations have already found the same answers. A universe of parallel solitudes, each one complete in itself, each one finite, each one ending when its star dies and its world grows cold without ever having touched another. And yet there is another scenario, equally consistent with the silence we observe, darker in some ways, more hopeful in others. Perhaps faster than light travel is possible. Perhaps the barriers we have been examining, the energy requirements and the exotic matter and the causality violations, are not fundamental prohibitions, but engineering challenges. Perhaps they yield not to our current technology, but to some future understanding that we cannot yet imagine. Perhaps somewhere in the galaxy, perhaps many places, civilizations have found the key, have solved the equations in ways we have not yet thought to try, have discovered the physics beneath the physics, the deeper theory that makes warp drives or wormholes, or some mechanism we have not yet named into practical realities. And perhaps those civilizations are not silent. Perhaps they are traveling, meeting, building something together, a network of worlds linked by faster-than-light ships, a community of intelligence spanning thousands of light years, having conversations that take days rather than millennia, sharing knowledge and art and science and history across the gulf that once seemed absolute. Perhaps we are simply not yet part of it. Perhaps we are too young, too primitive, too recently arrived at the level of technology needed to be noticed or to participate. Perhaps the galaxy's civilization, if it exists, looks at Earth the way we might look at a world where the first primitive cells have just appeared in the ocean, with interest, with patience, With the understanding that time is long and development is slow, and that in 1 billion years, if the planet survives, something extraordinary might emerge. Perhaps we are at the very beginning, or perhaps we are alone in the way that matters most. Not in the sense that no other life exists anywhere in the universe, for that seems nearly impossible given the universe's size and age and the apparent ease with which chemistry becomes biology, but alone in the deeper sense, alone in our inability to reach or be reached, alone in the silence that the speed of light enforces, alone with our questions in a universe that offers answers only to those who can travel far enough to find them. We do not know which of these pictures is true. We do not know whether the silence above us reflects an empty galaxy or a full one. We do not know whether faster-than-light travel is the missing piece that would transform isolation into connection, or whether the isolation is permanent, written into the structure of reality at a level that no future physics will ever overturn. What we know is the silence. What we feel on certain nights, looking up at the stars scattered across the dark, is the weight of it. And what we do not yet know is whether that silence will last forever. There is a place where our best theories go to die. It is not a location you can visit. It is not a laboratory or an observatory or a coordinate on any map. It is a conceptual boundary, a threshold beyond which the two greatest intellectual achievements in the history of physics stop working and begin to contradict each other in ways that produce nonsense. Infinite quantities where there should be finite ones, probabilities greater than one, energies that grow without bound, mathematical expressions that do not merely give wrong answers but give answers that have no meaning at all. This boundary is called the Planck scale, and it sits at the heart of everything we do not yet understand. General relativity, Einstein's theory of gravity, is one of the most precisely tested and spectacularly successful theories ever devised. It describes the large-scale structure of the universe with an accuracy that borders on the miraculous. It predicted that massive objects would bend the path of light passing near them, and in 1919, during a solar eclipse, Arthur Eddington measured the deflection of starlight around the sun and found it matched Einstein's prediction almost exactly. The observation made Einstein famous overnight, his face appearing on the front pages of newspapers around the world. He was, in that moment, the most celebrated scientist alive. But that was a simple test compared to what followed. General relativity predicted that accelerating massive objects would produce ripples in the fabric of space-time, gravitational waves, propagating outward at the speed of light like ripples on a pond. For decades, this prediction was considered almost untestable, the waves too faint, the instruments needed to detect them inconceivably sensitive. In September 2015, the LIGO detector in Louisiana registered a distortion in space-time smaller than 1/10,000th the diameter of a proton. The signal lasted a fraction of a second. It had been produced 1.3 billion years earlier by two black holes, each roughly 30 times the mass of our Sun, spiraling together and merging in a collision of unimaginable violence. The gravitational waves from that collision had traveled 1.3 billion light-years and arrived at Earth as a whisper so faint it strained the limits of human instrumentation. General relativity had predicted the existence of gravitational waves in 1916. It had predicted their precise waveform as a function of the masses involved and their orbital parameters. The signal LIGO detected matched those predictions with extraordinary precision. 100 years after Einstein wrote the equations, the universe confirmed them again. General relativity also predicted black holes, and we have now photographed them. In April 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the dark region at the center of the galaxy M87, 55 million light-years away. The size and shape of the shadow matched the predictions of general relativity almost exactly. In 2022, the same collaboration released an image of the black hole at the center of our own galaxy, Sagittarius A star, 27,000 light-years away, weighing approximately 4 million solar masses. The theory works. Everywhere we have tested it, at every scale, in every physical situation accessible to our instruments, it gives the right answer with extraordinary precision. And yet it is broken. Not in the way a damaged tool is broken, still functional but imperfect, broken in a deeper sense, broken in a way that the theory itself acknowledges, that appears explicitly in its own equations, as a signal that something is fundamentally incomplete. The breakage appears at singularities, points in space-time where the curvature becomes infinite, where the density of matter becomes infinite, where the tidal forces become infinite, where every physical quantity that the theory describes diverges to values that have no physical meaning. Singularities appear at two places in the universe as we currently understand it: at the center of black holes, hidden behind event horizons, inaccessible to any external observer, and at the beginning of time itself, at the moment of the Big Bang, when the entire universe was compressed into a state of infinite density and infinite temperature and infinite curvature. At both locations, general relativity's equations produce infinities and stop giving answers. The theory reaches the edge of its domain of validity and breaks down. This is not a failure of our mathematical techniques or our computational power. It is a signal that the theory is incomplete, that at the extreme conditions of a singularity, where both gravitational effects and quantum effects are simultaneously important, general relativity is simply the wrong description of reality. A better theory is needed. That better theory is what physicists call quantum gravity, a framework that describes gravity in the language of quantum mechanics, that tells us what space-time looks like at the smallest possible scales, that resolves the infinities at the center of black holes and at the beginning of time into finite, meaningful, physically real quantities. We do not have this theory. We have been working on it for nearly a century. The greatest minds in theoretical physics have devoted their careers to it, and it remains unsolved, not nearly solved, not solved in outline with the details remaining to be filled in. Fundamentally, genuinely unsolved in a way that suggests the solution will require ideas we have not yet had. The difficulty is not merely technical, it is conceptual. General relativity and quantum mechanics are not just different theories that need to be combined. They are built on different foundations, describe the world using different mathematical structures, and make assumptions about the nature of reality that are mutually incompatible. General relativity describes a smooth, continuous spacetime, a four-dimensional fabric that curves and bends in response to matter and energy. In general relativity, spacetime is the stage, and everything else happens on it. Space and time are real, physical entities that have properties and can change. Quantum mechanics describes a world of discrete, probabilistic events. Particles do not have definite positions and momenta simultaneously. They exist in superpositions of multiple states until measured. The outcome of any measurement is fundamentally random, governed by probabilities that the theory predicts with extraordinary precision, but that cannot be reduced to underlying deterministic causes. In quantum mechanics, the concept of a smooth, continuous background spacetime is assumed but never explained. The stage is taken for granted. When you try to apply quantum mechanics to spacetime itself, treating spacetime as a quantum field like the electromagnetic field or the electron field, the mathematics produces infinities at every step. The energy of empty space diverges. Virtual particles contribute infinite amounts to every physical quantity. The theory becomes unpredictable, generating answers of infinity for questions that should have finite answers. The techniques that work for other quantum fields, a mathematical procedure called renormalization that tames infinities by absorbing them into measured physical parameters, fail for gravity. Gravity is not renormalizable in the way that the other fundamental forces are. The infinities that appear in quantum gravity cannot be absorbed and cancelled. They persist, grow worse at higher energies, and ultimately render the theory meaningless. This is the problem of quantum gravity in its technical form, and it has resisted solution for a very long time. The most developed candidate for a solution is string theory. String theory proposes that the fundamental constituents of reality are not point particles, dimensionless dots with no spatial extent, but tiny one-dimensional objects called strings, loops or segments of energy so small that the Planck length, 10 to the power of negative 35 meters, is their natural size. Different vibrational modes of these strings correspond to different particles. An electron is a string vibrating in one pattern, a quark is a string vibrating in another, a photon in another still. And one of the necessary vibrational modes of a closed string, a loop rather than a segment, corresponds to a particle with exactly the properties that a graviton, the hypothetical carrier of the gravitational force, must have. String theory does not need gravity to be put in by hand. It predicts gravity. It requires gravity. The theory cannot be formulated without it. This was the discovery, made in the mid-1970s, that transformed string theory from an interesting curiosity into a serious candidate for a theory of everything. String theory also requires additional spatial dimensions. 6 or 7 extra dimensions, compactified at each point in space into shapes so small they have never been detected. The geometry of these compactified dimensions determines the properties of particles in our three-dimensional world. Different compactification geometries give different particle masses, different charges, different force strengths, and there are an enormous number of possible compactification geometries. Estimates run into the tens of hundreds of digits, each one giving a different set of physical parameters. This is both a feature and a problem. A feature because it means string theory is rich enough to potentially describe any universe, including ours. A problem because the number of possible descriptions is so large that the theory seems to lose predictive power. If string theory is compatible with virtually any set of physical parameters, how do we test whether it describes our specific universe? How do we distinguish it from other theories that are also compatible with our observations? This question has not been answered. String theory has been developed mathematically into an extraordinarily sophisticated framework with deep connections to other areas of mathematics and physics that suggest it is capturing something real about the structure of reality. But its direct experimental predictions, the things it says that are different from what other theories say and that could in principle be tested, remain either at energy scales far beyond our current accelerators, or so subtle that distinguishing them from other theories is not yet possible. Loop quantum gravity takes a completely different approach. It keeps the particle-based description of matter from quantum mechanics and applies quantum principles directly to space-time itself, rather than introducing new fundamental objects like strings. In loop quantum gravity, space-time at the Planck scale is not smooth and continuous, but granular and discrete. Space is made of finite indivisible quanta, the smallest possible volumes, each of Planck scale size. Time advances in discrete ticks rather than flowing continuously. Below the Planck scale, the concepts of distance and duration simply cease to apply. Space and time are not fundamental. They emerge from something deeper, a network of quantum relationships that does not itself exist in space or time. Loop quantum gravity has achieved some results that string theory has not. It provides a consistent description of the interior of black holes that avoids singularities. Instead of infinite density at the center, the theory predicts that quantum gravitational effects create an enormous pressure at Planck densities that halt the collapse and bounce the matter outward. The singularity is replaced by a transition to another region of space-time, perhaps another universe, perhaps a new expanding region branching off from our own. It also provides a model of the Big Bang as a big bounce, a transition from a previous contracting phase of the universe to our current expanding phase. The moment of the Big Bang, where general relativity predicts infinite density and the beginning of time, is replaced in loop quantum gravity by a moment of maximum density, finite and calculable, after which the universe began expanding again. Time did not begin at the Big Bang, it continued through it from a previous epoch. These are remarkable results, but loop quantum gravity, like string theory, remains unproven. Its predictions are at energy scales we cannot test. Its mathematical development is less complete than string theories, and it has not yet been shown to reduce to general relativity at large scales and low energies in a fully rigorous way. The theory is incomplete. Both approaches, and the many others being developed by physicists around the world, share a common feature. They change the description of space-time at the smallest scales. They say that the smooth, continuous four-dimensional manifold of general relativity is not the fundamental reality. It is an approximation, valid at the scales we can observe, that breaks down when you look closely enough. The true nature of space-time is something different, something stranger, something that our current mathematics can only partly describe. And here is why this matters for everything we have been discussing tonight. Every conclusion we have drawn about the impossibility or extreme difficulty of faster-than-light travel is based on our current theories, on general relativity and quantum mechanics and their combined, incompatible descriptions of the universe. These theories are incomplete. We know they are incomplete because they contradict each other at the Planck scale. We know they are incomplete because they predict singularities where there should be physical answers. We know they are incomplete because there is a whole regime of physics, the quantum gravitational regime, where we have no reliable theory at all. In that regime, the rules might be different. Consider what happened when quantum mechanics replaced classical physics in the early 20th century. Classical physics, the physics of Newton and Maxwell, was extraordinarily successful. It described the motion of planets, the behavior of fluids, the propagation of electromagnetic waves, the operation of heat engines, with an accuracy that seemed almost complete. Physicists at the end of the 19th century had genuine reason to believe they were approaching a final, complete description of reality. The major laws had been discovered. What remained was to fill in the details. Then the details turned out to be wrong. Classical physics could not explain the spectrum of light emitted by hot objects. It could not explain the photoelectric effect. It could not explain the stability of atoms, which by classical electromagnetism should collapse as electrons spiraled into the nucleus in a fraction of a second. These were not minor discrepancies. They were fundamental failures. Quantum mechanics was the response, and it did not simply correct the classical laws. It revealed an entirely different layer of reality, one that operated on principles that classical physics had not imagined and could not have predicted. Superposition, entanglement, fundamental uncertainty, wave-particle duality, the discreteness of energy and angular momentum, the probabilistic nature of physical reality at the quantum scale. None of these features are present in classical mechanics. They are not approximations to classical results or limiting cases of classical behavior. They are genuinely new. They describe a world that is, at its deepest accessible level, profoundly different from the world that classical physics described. General relativity did something similar to our understanding of space and time. Before Einstein, space was absolute, fixed, the same for all observers. Time was universal, flowing identically everywhere. These were not merely convenient assumptions. They were considered obvious features of reality, so obvious they did not need to be stated. Newton's equations assumed them without comment. Einstein showed they were wrong. Space and time were relative, flexible, observer-dependent, woven together into a dynamic space-time that responded to matter and energy. The universe was far stranger than anyone had imagined, and the strangeness had been there all along, hidden in the mathematics, waiting to be seen. A theory of quantum gravity will almost certainly reveal another layer of strangeness, another set of features that our current theories do not contain and cannot predict. The behavior of space-time at the Planck scale may be so different from the behavior we are familiar with that conclusions drawn from our current theories about what is and is not possible may need to be revised fundamentally. This does not mean faster-than-light travel will turn out to be possible. The new physics might make the barriers more absolute, not less. It might provide a rigorous proof that causality forbids superluminal travel in any form, under any circumstances, a proof that our current theories cannot supply because they are not complete enough. The quantum gravity theory might close the door more firmly than it was closed before, or it might open a window. It might reveal that space-time at the Planck scale has a structure that allows connections between distant points, shortcuts that do not exist in the smooth manifold of general relativity, but emerge from the discrete quantum geometry of the true theory. It might show that negative energy can be produced in greater quantities than classical calculations suggest, by exploiting features of the quantum vacuum that our current theories miss. It might provide a description of wormholes or warp metrics that is free of the instabilities and causality violations that plague them in general relativity, because the deeper theory handles singularities and extreme curvatures in a way that general relativity cannot. We do not know. We genuinely, completely, honestly do not know. And anyone who tells you they do know, who tells you with certainty that faster than light travel is forever impossible, or who tells you with certainty that we will one day build a warp drive, is telling you something they cannot actually know, because the theory that would settle the question does not yet exist. What we can say is this: the history of physics is a history of surprises. A history of the impossible becoming possible when someone asked a slightly different question, or looked at a familiar problem from a new angle, or discovered that the equations contained a chapter everyone had overlooked. A patent clerk in Bern who watched a tram pull away from a clock tower and wondered what the world would look like if the tram were traveling at the speed of light, and in that wondering restructured the foundations of physics so completely that the science before and after him are almost unrecognizable as the same discipline. A graduate student in Wales who watched a television program about a fictional starship and asked whether the mathematics of general relativity, the same equations that imprisoned us within the speed limit, also contained a description of how to circumvent it, and found that they did. The universe has surprised us before. It has revealed itself to be stranger and richer and more intricate than any of our theories predicted. And there is no particular reason to believe that we have now, finally, at last, reached the end of surprises. That the physics we have is the physics there is. That the strangeness stops here. The Planck scale is waiting. The quantum gravity problem is waiting. The reconciliation of our two greatest and most mutually incompatible theories is waiting. And in that waiting, in that unresolved tension between what we know and what we do not yet know, there is space. Not the space of empty optimism or wishful thinking, but the space of genuine, rigorous, mathematically grounded uncertainty. The space where physics lives before it becomes physics. The space where the next surprise is hiding. We do not know what it is. We do not know when we will find it. We do not know whether it will change the answer to the question we have been asking all night. But we are looking. Step outside tonight, if you can. Find a place away from the lights of the city, somewhere the sky is dark enough to show you what it actually contains. Lie down on the ground if you are willing. Let the earth hold you. Let the sky open above you until it is all there is, the darkness and the points of light scattered across it like the remnants of something shattered long ago. Look at it for a long time, long enough for the scale to begin to register, long enough for the distance to start to feel real rather than merely numerical. Every point of light you can see with your naked eye is a star in our own galaxy. The farthest ones visible without a telescope are roughly a few thousand light years away. The light entering your eyes right now left those stars before any written language existed on this planet. Before the pyramids, before the first city, before human beings had yet conceived of the idea of writing down what they knew so that others might read it after they were gone. That light has been traveling through the void for thousands of years and has arrived at this exact moment at the surface of your eye, where it will be converted by the chemistry of your retina into an electrical signal that your brain will interpret as a tiny point of brightness in the dark. You are the end point of a journey that began before civilization. That is what it means to look at the night sky. Now consider what lies beyond what you can see. The stars too faint to register without instruments. The 100 billion or more stars in our galaxy alone, each one a sun, many of them circled by worlds. The edge of the Milky Way, 100,000 light years away. The Andromeda Galaxy, a smear of ancient light 2.5 million years old. The galaxy clusters and superclusters extending outward in every direction for billions of light years. The edge of what we can observe, 46 billion light years away in every direction, a sphere of ancient light centered on this planet, not because we are special, but because this is where we happen to be standing. And beyond even that, almost certainly, more space, more stars, more worlds, perhaps infinitely more, stretching on in directions we cannot see, filled with matter and light and possibly life, all of it forever beyond our observational horizon, forever unreachable even by the light we send outward tonight. This is the universe we live in. This is the scale of the problem we have spent tonight examining. We began with a speed, 186,282 miles per second, the fastest anything can move through space, the universal speed limit, confirmed by every experiment ever conducted, written into the mathematical foundations of reality with a firmness that has not yielded to a century of scrutiny. We examined why this limit exists, following Einstein's reasoning from its strange starting point, the constancy of the speed of light for all observers, through its stranger implications, the flexibility of time and space, the impossibility of reaching light speed for any object with mass, the infinite energy required to approach it. We found a loophole. A young physicist watching a television program asked a question no one had thought to ask before, and discovered that the same equations imprisoning us within the speed limit also described a mechanism for circumventing it, not by moving through space faster than light, but by moving space itself, the warp bubble, the Alcubierre metric, a valid solution to Einstein's field equations, mathematically rigorous, physically extraordinary, describing a spacecraft that sits perfectly still while space-time contracts ahead of it and expands behind it, carrying it to the stars not by traveling, but by being carried. We examined what it would cost. Energy requirements that began at the mass of the observable universe and were reduced through decades of theoretical refinement to something still enormous but at least finite and nameable. We found that the drive requires negative energy, a quantity that sounds impossible but is real, demonstrated in laboratories through the Casimir effect, existing in the universe in tiny, measured, confirmed amounts. We found that the gap between the tiny amounts we can produce and the vast amounts the drive requires is a gap that no current theory tells us how to close. We found the deepest problem, that faster-than-light travel by any mechanism in any form leads through the mathematics of special relativity to the possibility of time travel, of closed, time-like curves, of causes following their effects, of the logical structure of reality, folding back on itself in ways that generate contradictions the universe appears constitutionally unwilling to permit. We found that the universe may be enforcing its speed limit not through a single prohibition but through a conspiracy of physical consequences, each one independently arriving at the same conclusion, each one saying that this particular door does not open, that this particular path does not lead where you want to go. We looked for other doors, wormholes, those tunnels through the geometry of space-time predicted by the very equations that describe black holes, requiring the same exotic negative energy, suffering the same causality problems, adding the additional difficulty of placement, of how you get one mouth to its destination before you can use it to make the journey fast. Quantum entanglement, real and instantaneous, and profoundly strange, but carrying no information, allowing no communication faster than light, offering the appearance of superluminal connection while delivering nothing that could be used for travel or transmission. Extra dimensions, the hidden geometry of string theory's compactified spaces, potentially offering shortcuts through a bulk we cannot access, depending on physics we have not confirmed and mechanisms we cannot describe. We found, at the end of every path, a wall. But we also found something else. We found that the walls are built from theories we know are incomplete, that the regime where the speed limit is most strictly enforced, where the barriers are most absolute, where the mathematics breaks down most catastrophically, is precisely the regime where our theories fail, where general relativity and quantum mechanics contradict each other and produce infinities and cease to give answers, where a deeper theory, a theory of quantum gravity we do not yet possess, would need to take over. And in that gap, in that genuine, rigorous, mathematically grounded region of ignorance, the question remains open. Not because of wishful thinking, not because we prefer a universe where the stars are reachable, but because the tool we would need to answer the question definitively does not yet exist. We cannot say with certainty that faster-than-light travel is forever impossible, because we do not have the complete theory of physics that would let us say so with certainty. What we can say is that every path we have found toward it is blocked, and that the blocking may be fundamental, and that we do not know. This is an unusual position for science to be in. Science prides itself on definitive answers, on the accumulation of knowledge that reduces uncertainty, on the replacement of ignorance with understanding. But at the frontier, at the edge where the known gives way to the unknown, uncertainty is not a failure. It is the honest description of where we stand. We are at the frontier. The question is genuinely open, and genuinely open questions are among the most precious things the universe offers us. Consider what it means that we are asking this question at all. There is a planet in this galaxy, one planet among the hundreds of billions that almost certainly exist, where a species of primate has been alive for roughly 300,000 years. For most of that time, these creatures had no concept of what the points of light in their night sky actually were. They told stories about them, they worshipped some of them, they used them for navigation, but they did not know that each one was a sun, vast and ancient, burning through nuclear fusion at temperatures that would vaporize any matter we know of in an instant. Then, in a period that amounts to an eye blink in the history of this species and less than an eye blink in the history of the universe, everything changed. These creatures developed a method for testing ideas about the world against the evidence the world provides. They called it science, and using this method, in a few centuries, they learned more about the nature of reality than in all their previous history combined. They learned that the Earth circles the sun, not the other way around. They learned that the sun is a star, ordinary in most respects, one of hundreds of billions in a galaxy that is itself one of trillions. They learned that space and time are not absolute but relative, woven together into a dynamic fabric that bends and warps in response to matter and energy. They learned that matter is made of atoms, that atoms are made of smaller particles, that those particles interact through fields that permeate all of space, that the vacuum itself seethes with quantum fluctuations, that empty space is never actually empty. They learned, from the light that reaches them across billions of light years of void, that the universe began in a state of almost unimaginable density and heat, and has been expanding ever since, cooling as it expands, its matter clumping under gravity into stars and galaxies, and the intricate web of structure that fills the observable cosmos. They measured the age of the universe. They measured its size. They measured the rate at which it is expanding and found, to their astonishment, that the expansion is accelerating, driven by something they cannot see or measure directly, something they call dark energy, because they do not yet understand what it is. They sent machines beyond the edge of their solar system, small devices built from refined metals and semiconductors and the accumulated knowledge of thousands of scientists and engineers traveling for decades through the cold between the stars, sending back radio signals that took hours to arrive. One of those machines, called Voyager 1, has now crossed the heliopause, the boundary where the sun's influence gives way to the interstellar medium, the true beginning of the space between stars. It is the farthest any human-made object has ever traveled. It carries a golden record, a disk containing sounds and images from Earth, a message to whatever might someday find it in the darkness between the stars. These creatures, this species, have looked at the universe and measured it. They have taken its dimensions, they have determined its age, they have identified its composition. They have decoded the language in which its history is written, the light that carries information from billions of years ago, from billions of light years away, arriving at this small world and being read, interpreted, understood, and now they are asking whether they can reach it, whether the distances that dwarf their every achievement are permanent features of their situation, or challenges that a sufficiently deep understanding of physics might someday overcome, whether the universe they have measured so carefully is a prison or simply a very large room whose locks they have not yet learned to open. We are those creatures. You are one of them, and you are doing, right now in this moment, the thing that makes that species extraordinary. You are thinking about it. You are holding the question in your mind, turning it, examining it from different angles, following its implications into territory where certainty runs out and wonder begins. You are doing what humans do that no other species on this planet has ever done, so far as we know. You are contemplating your own smallness against the scale of what exists, and finding in that contemplation not despair but curiosity. Not resignation, but the specific kind of restlessness that has always preceded discovery. The nearest star is 4.24 light-years away, a distance so vast, has ever traveled more than a fraction of a percent of the way toward it. The observable universe extends 46 billion light-years in every direction. The speed of light is both the fastest messenger we have and the most formidable barrier we face. The warp drive works on paper and fails in practice. The wormhole is permitted by the equations and forbidden by the physics. The entanglement is real and instantaneous and carries nothing we can use. Every path is blocked, and we are still looking. That is not nothing. That is, in fact, almost everything. The looking is what matters, the refusal to accept the size of the problem as a reason to stop asking. The willingness to sit with a question that may not have an answer in our lifetimes, or in the lifetimes of anyone alive today, and to keep working on it anyway, because the question is real, and the universe is under no obligation to make its secrets easy to extract. There have been other moments like this in the history of science, moments when the question seemed too large, the barrier too high, the problem too fundamental, when the impossibility seemed absolute and the tools available seemed laughably inadequate to the challenge. And then something changed. Not always in the direction people expected, not always with the solution they were looking for, but something changed. A new question was asked, a new angle was found, a new layer of reality was uncovered that made the old barriers look different, sometimes smaller, sometimes more absolute, but always different from what they had seemed before. We do not know what the next change will be. We do not know when it will come. We do not know whether it will open the door to the stars or close it more firmly than before. We are at the beginning of a journey whose destination we cannot see from here. We are standing at the edge of the firelight, looking out into the darkness beyond, where the answers to the questions we most want to ask are hiding in a silence that we do not yet have the instruments to break. The light from Proxima Centauri left its source 4 years and 3 months ago, and is arriving at this planet right now, at this moment, at the speed that nothing can exceed. It crossed 4 light-years of emptiness to reach you, 4 light-years of cold and silence and the deep dark between the stars, and it arrived. It always arrives. Light always completes its journey. It does not stop because the distance is large. It does not slow because the void is vast. It does not lose its way in the dark. Perhaps that is the most honest thing the universe has shown us tonight. Not that the stars are reachable, not that the barriers will fall, but that across any distance, through any darkness, through 4 years of emptiness or 13 billion years of cosmic history, light arrives, diminished, ancient, but present, a signal that something is out there, still burning, still sending, and we are here, on this small, warm world, holding our instruments up to the sky, listening,